Alright, in this video I'm going to discuss the speed of sound in different medium. The speed of sound varies greatly depending on the type of medium. In solids and liquids, the speed of sound is very fast. If you remember, a sound is a local area of high density followed by an area of low density, so it's a compression or rarefaction, that spreads throughout the material. In solids and liquids, there are large intermolecular forces. There are a lot of interactions between the particles, and as a result, when those particles are undergoing a lot of interactions, that means that the disturbances in the particles can spread through the material quickly. There's a lot of contact between the materials, so if there's a compressed area, it can push on the rarefacted area very effectively, and as a result, the speed or the sound will travel through the material very quickly. We can see just a couple of examples here. In water, the speed of sound is 1,400 meters per second. In steel, it's like 6,100. Those are just sort of median values that I took off the internet out of ranges. In air, again, and just as a typical value, the speed is about 340 meters per second. The speed of sound in air is much lower than it is in water or steel because air particles spread out to fill their container. We have to have the air molecules actually collide for the areas of compression and rarefaction to spread throughout the material, so it takes a little bit more time. Obviously, it's still very fast. As a specific example, we're also going to talk about the speed of sound on a string. So what I'm imagining here is a string that's fixed between 2 points like that, and if a wave is created on it, let's say you push it up and down like that, the wave's going back and forth. How fast is that wave going to go back and forth? What is the speed of sound on that string? It depends on the linear density. To understand why it depends on the linear density, it helps us to remember Newton's second law. Newton's second law has two main points. The acceleration is directly proportional to the force, and the acceleration is inversely proportional to the mass. If we imagine for the string to get vibrating, it must accelerate, then we can say the speed is going to be related to the acceleration. So this is going to be like the speed, not exactly the same as the speed, but sort of like it. So if we increase the force or we increase the tension on the string, we should increase the acceleration, and as a result we should increase the speed. So as the force of tension goes up, the velocity of sound on that string should go up. We understand this, or we've seen this in the everyday world, when we tighten a guitar string. When you tighten a guitar string, you're increasing the tension on that string, and the increased tension on that string will cause the velocity and as a result the frequency of the string to increase. Alternatively, the acceleration is inversely proportional to the mass. That means as the mass of the string goes up, the velocity on the string will go down. It's not the exact mass really that matters, it's the mass per unit length, or the linear density. Again, when we think of a guitar, we can understand this when we imagine the thick strings that make up the lower key or the lower strings on a guitar versus the thin strings which make up the higher tones or frequencies on the guitar. So as the string gets thinner, that means its linear density goes down, the resulting speed on the string goes up, and so we get a higher frequency. Or I guess if you want to follow it as it's written here, as the strings get thicker, the speed of sound on the string gets lower, and as a result the overall frequency of the string will decrease. The actual equation shows a square root relationship between the two things, but it does show the expected relationship. So as the velocity goes up, or as the force of tension goes up, the velocity will go up. Also, as the linear density goes up, the velocity will go down. It's just a square root in that relationship. This is an interesting one because it looks complex and we want to make sure it works out from a unit perspective. Remember that the force of tension will be measured in newtons, and the linear density will be measured in kilograms per meter. And if we recall then that a newton is equal to 1 kilogram meter per second squared, and we divide that by kilograms per meter, then the kilograms will cancel out, the meter from the bottom will go all the way up to the top, and when we square root, then what we're left with is just meters per second. So it's kind of neat the way the units work out for that equation. So the speed of sound increases as there's more interaction between the particles. Air is slower than water, where there's more interaction, which is slower than something like steel, where there's a lot more interaction. And if we take that steel and we stretch it into a string, then we can figure out that the speed of sound on that string is going to be equal to the force of tension. The faster it gets pulled back to its median position, it's going to make it vibrate faster, and inversely proportional to its mass due to the increased inertia.